Okay, can everybody hear me now again?
Yeah.
Okay, good deal. Looks like I'm good to go here. Let me just get into here. I'm gonna go. I think you guys left off with hydraulics. Is that correct?
Yes.
Okay, good. All right, everybody can see that coming up. Okay, good deal. So, well, let's talk about hydraulic systems in the CRJ 700. So, the plane, the CRJ 700, is equipped with three independent hydraulic systems. Okay, so this first bit of information here is going to be stuff you are going to want to know. Okay, this is what we want to know about the hydraulic key points. When you have your systems quiz, this will be on the quiz. Okay, so there are three hydraulic systems. Each one of those systems has two hydraulic pumps. Okay, so three systems, and each system has two pumps. So that makes six pumps total, six hydraulic pumps, two for each system. There's three systems. The main pumps, we call those the A pumps. Okay, and then the backup pumps we call the B pumps. So for each system, there's essentially system one has its A pump and a B pump. So you'll hear these pumps referred to as 1A or 1B or 2A and 2B, 3A and 3B. All that really means is that it's system 1 pump A or system 2 pump B, system 3 pump A or B. So just so it makes sense as we go along here, but the A pumps are your normal system. They supply normal system pressure. Okay, so pumps 1A and 2A are engine driven pumps. And then 3A is an electric pump. And then our backup pumps, referred to as the B pumps, they supply supplementary pressure during takeoff, landing, or when manually selected by the pilot. Pumps 1B, 2B, and 3B are all electric pumps. So as you guys have been going through the systems, you've probably been seeing that with a lot of these systems, there is a lot of redundancy. Okay, and that's obviously a common theme in any aircraft is redundancy. Um, the FAA requires a lot of redundancy in airplanes in order to certify those planes as Part 121 aircraft. In order to be able to fly 121 service, fly revenue passenger service, they have to be safe. And part of being safe is having redundant systems in all of the planes. So now, when you talk about the hydraulic system, no difference there. It's got three completely independent hydraulic systems. Each one of those systems has the capability of supplying hydraulic pressure to the entire plane, or at least to the systems necessary to fly the plane and land safely in the event of an emergency. So if you were to have one or two of these systems fail, you can still have the necessary hydraulic pressure supply with just one of them operating. So let's talk about system one and system two. So those are your normal systems. I mean, like when the plane is up and it's functioning and it's flying and doing everything it's supposed to, you're really just using pumps 1A and 2A. And systems 1 and 2 are really the only ones that are being used. System 3 is a completely backup system. Okay, it's really just there to supply additional pressure, hydraulic pressure, when needed, or in the event that hydraulic system 1 and 2 fail. Okay, so going back where it says pumps 1A and 2A are engine driven, that would mean that if that engine, so there's basically one pump for each engine. So, pump 1A and 2A. Now, if, let's say, one of those engines fails, then that hydraulic pump associated with the engine that failed will no longer work. If you were to have a dual engine failure, then both pumps 1A and 2A would not work. Okay, but pumps 1A and 2A, the one of the things you'll want to know and understand is that, where it says here, pumps 1A and 2A are engine driven, and all the rest of the 4 remaining hydraulic pumps are all electric driven pumps. So 2 that are engine driven and 4 that are electrically driven. Okay, if you look at system 3, which is really the backup system, both pump 3A and 3B are both electric. So the entire system 3, both pumps are electric. Okay, so system 3 does not rely on the engine, on either of the engines at all for its to be powered and to supply hydraulic pressure. So the big issue is if you have engine failures, 1 or 2 engine failures, hopefully, one engine failing, not going to say it's common, but, in the case of SkyWest Airlines, they fly anywhere from 2,000 to 2,000 to 2,500 flights a day. Back when I was working there, I would see, based on that volume of flying, you're talking, in the neighborhood of, usually anywhere from 60 to 70,000 flights a month. You'll see, anywhere from 3 to 6 engine failures a month based on, 60 to 70,000 flights. So you can kind of see the statistics there. It's kind of rare to see. So the one thing, when we're talking about the role of the dispatcher and whether it be, especially when you start talking about systems, the one thing that I like to touch on as far as one of the big differences from a dispatcher's perspective as compared to a pilot's perspective. Okay. Now a pilot, he goes through all of, he knows the systems, he knows, the hydraulic systems, the system 1, 2, what they do, how they're engine driven, electrically driven. They know all of the stuff there too. Okay. The dispatcher knows what he needs to know as far as, what concerns him and the things that are dispatch related. But when you start talking about issues with systematic stuff, anything that you've learned about, whether it's a hydraulic system, air conditioning system, pressurization, any system that we'll talk about, when there are issues with those systems, you're going to find out very quickly that the dispatcher is usually going to be the more knowledgeable person when it comes to the dispatcher and the pilot. And it's not because the pilots don't know about them or whatever, but when there's issues, and it's not so much like about the system itself, like the dispatcher doesn't necessarily know more about the system, but when something goes wrong, when something fails, when there's an emergency, that's when the dispatcher is usually going to be the more knowledgeable person. You'll talk to pilots, and I used to make a habit of it when pilots would come through the SkyWest OCC and they would be doing tours and stuff. I would make a habit of asking them. I had several different questions that I would ask them, but one of them was, "Did you ever experience an engine failure?" Okay. If you were to ask that question to, if 80% of the pilots that you ask that question to are usually going to say no. Most pilots go their entire careers without ever having an engine failure. Okay, so when you do have an engine failure, because it's so rare for a pilot to see it, they're usually not going to be well versed in what the procedures are. When a hydraulic system fails, once again, very rare. They're not going to necessarily know what the procedures are. Okay? Dispatchers, on the other hand, now the ratio, like I said, is still very low. And like I said, I would see, 5 a month maybe, but, 5 out of 70,000, 5 out of 60,000. So it's still really low statistics, but, you'll see 5 a month. Not individually as a dispatcher. Now, I had a little bit of a different perspective because I was the shift manager. So if it happened at all to any SkyWest flight, I would see it and I would deal with it, right? So now you'll go through your dispatch career and you'll be in different positions where you'll see stuff more often and not as much, but you will see these as dispatchers as well. Don't be fooled. I mean, if the company itself has 5 or 6 a month, eventually you're going to have a couple a year probably that you'll have personally that you'll have to deal with. Now, if you become a system controller or a shift manager, then you'll see it a lot more frequently as well, just depending on the nature of your job. But as a shift manager, especially, I was seeing, you start to count the numbers up, even though it's 4 or 5 a month or 6 a month. Over the space of a year, 2 years, 3 years, you'll see several hundred. Okay, so you'll have a lot of experience, even though it's a very rare thing. You'll have a lot of experience as you go throughout your careers of dealing with system failures, engine failures, honestly, any type of emergency you can think of. Any type of a diversion, medical diversions, medical emergencies, mechanical emergencies, diversions, mechanical diversions, anything that you can think of. Now, that's where the dispatcher picks up a huge chunk of your knowledge base. That is part of where you are relied on by the pilots. That's where your operational control really plays a very important role in your job. Okay, that's why you have 50% of that operational control, is because even though you're not up there flying the plane itself and making those decisions, you, in emergency situations, you are usually going to be the lead person. Okay, the pilot, the captain is usually going to defer to the dispatcher on what they need to do, where they need. Now they're going to go through their what we call their QRH. Anytime they have any sort of a scenario going on, they open up we call it the quick reference handbook, but it's just basically whatever the nature is, they can look it up and then it'll give them a list of instructions on what they need to do. However, outside of what it says in that QRH, it's nothing that they're going to have memorized, and they're going to have to open up their tablets and bring up this QRH document and go through it, but outside of that, they're not going to necessarily know what to do, and they're going to rely heavily on the dispatcher as far as all of the decision making from that point forward. Where are we going to go? What do we need to do? Do we need to descend in altitude? I mean, just depending on what it is. But that's where the dispatcher plays a huge role, and that's where your knowledge of systems, emergencies, or any other thing that can happen up there in the air, becomes very critical. And it even touches on what I was talking about a little bit ago, as far as, this class provides you with the basic foundation of what you need to get your license. Okay? But as you go through this, you'll pick up tidbits here and there that you don't necessarily need to get your license, but just stuff that we will talk about in here that, down the road, you're going to start learning about a lot more of this stuff, and you're going to remember that we talked about it and remember why it's important. But as you go through and you pick up this knowledge at, whether it be SkyWest or any other airline, or if you work at SkyWest for a while and then you go to a major airline and work there for a while, or if you come into the FAA like I did and work here, All of these different things, every airline you go to, every position you work in, your knowledge base is going to increase. And that's one of the beauties of this type of work that I really like, is that you never stop learning. And if aviation is something, that interests you, and I think that everybody in this class, aviation is an interest, I hope. But when you're surrounded by people that are aviation oriented and aviation is their passion, then you really enjoy doing this stuff, and you really enjoy picking up all of these tidbits of knowledge over the years of different scenarios. You'll start seeing things a lot, and when you go talk to pilots, a pilot can go, and going back to what I was saying about me asking those pilots the questions when they would come in on tours and stuff like that. I often would find pilots that had never gone, and we're talking 30, 35 years, 40 years of flying in the airline environment, and not one diversion, whether it be even for weather, but no mechanical diversion, no medical diversion, no weather diversions, their entire careers. That's thousands and thousands of flights, thousands of hours in the air, and not one diversion. It's crazy to think that that's even possible, but it is. Because if you look at SkyWest as a whole, okay, now I know I threw out those numbers earlier about, you might see 5 or 6 engine failures in 1 month out of 60,000 flights. Now take that same 60,000 flights on a monthly basis. Well, actually, let's just go all the way down to a daily basis. So if you got 2,000 to 2,500 flights a day, on any given day, SkyWest will have probably, and some days are worse than others, but at a minimum, I would say 1% of SkyWest flights divert on a daily basis. And that might be high, but I would say anywhere from 10 to 20 diversions in one day. Now that can be a mixture of weather, mechanical, medical, any reason. A diversion for any reason would count in this statistic here. But when you think about that, 1% or less per day of the total flight schedule will divert, then you can see why a pilot can go 40 years of flying in an airline and not divert, because every day he starts out with a 99% chance that he will not divert. So you start thinking about those numbers, because as a dispatcher, you live in a totally different world in the OCC. You see everything that can happen. You will see every emergency. You will see accidents. You will see crashes. You will see medical diversions, mechanical diversions, weather diversions, almost on a daily basis. You will see that. You will see all sorts of ATC issues and programs and cancellations and delays, and you pretty much deal with the crap. That's really what the OCC deals with. That it's the 1% of the flights per day that caused all the problems in the OCC. 1% of flights cause 95% of the work. So when your focus, and the dispatcher, obviously dispatchers plan all the flights, but a dispatcher, if you don't have an issue with a flight, if it doesn't divert or have a weather issue or something like that, then most of those flights are going to be easy to plan and do a dispatch release for and send out. So most of those will be easy to do. Some are harder than others depending on, weather, routing, and different things like that. But generally speaking, even as a dispatcher, if you're dispatching 50 flights in one day, 5 of those flights are going to be your problem flights. Okay, and I'm saying a problem, not even necessarily meaning that they'll divert or whatever, but they'll be ones that, you might have extra issues with or have to spend extra time on. Okay, so your focus as a dispatcher really is those problem flights. And whether it be the dispatcher, the shift manager, the system controllers, it's the 1% of the flights that cause all the work. So when you're focused, as you go through your careers of really focusing primarily, most of your work is your problem flights, then you're used to dealing with problems. You're used to seeing the problems. You're used to coordinating emergencies and all sorts of stuff like that. And so it just becomes, you think that it's just normal operation. Like that's just standard operating procedure for you is having issues. And so when you guys go and talk to pilots, without thinking about it, you assume that it's the same way for them. But then you start thinking about it and like, you know what? I mean, when 99% chance they're not going to have a problem on any given day, then you start to realize that they don't see any of this stuff. They to think that a captain can go his entire career without diverting even one time seemed, before I really started thinking about it, it seemed impossible. But when I started thinking about it, it's actually probable that it wouldn't happen. So keep that in mind. I don't mean to divert off topic, but the systems play a big role, and in your knowledge of systems and what you need to do when things go wrong is very crucial to your job, and you kind of become the quarterback. I mean, the flight, if everything's going good on the flight, you normally don't even talk to the crew. The pilot, the captain, when everything's good, the captain's in charge. He's the one handling it. He's the one, you're not going to hear a peep. He's not going to need your help. It's only when something goes wrong, really, that the dispatcher gets involved, or if something is about to go wrong, then it's almost kind of like the dispatcher steps in and takes over. You're not literally flying the plane, but you're pretty much giving orders on where that plane is going to go and what it's going to do and when it's going to do it. Okay? So just keep all that in perspective, because that is really the way it works. So when something goes wrong, the pilot's going to contact you and he's going to pretty much, tell me what to do. That's what's going to happen. He might send you an ACARS. He might call you over the radio. Either way, though, he's basically going to be like, hey, we've done this and this and this. We did what the QRH said. And like I said, the QRH is just basically the minimum criteria of like, hey, do this, shut off this, turn on that, shut off that. It's just a really small, quick list to make sure that that you don't, fall out of the sky, essentially. But it doesn't give you anything further than that. It gives you enough information to stabilize to the point where you can contact dispatch and figure out what you're going to do from that point. So when something goes wrong, it really is the dispatcher that kind of just takes things over, and in a literal sense, you kind of are flying the plane from the ground. You're just giving instruction on where it's going to go and where it needs to divert to or whatever needs to happen. But that's usually going to come from you, and you'll become the primary decision maker. Whereas everything up until that point, when everything was going smooth, the primary decision maker really was the captain. So anyway, let's go back to hydraulic systems here. So system 1 and 2 are the primary operating hydraulic systems when they're on, when the plane is flying and everything's going good. Those are the two systems being used. And system 3 is simply just a backup. And just remember that the 1A and 2A are engine driven, and then all of the other pumps are all electric. Okay, the backup pumps are really just used in the event that the primary 1A, 2A, or 3A pumps stop working. Okay, and then you kick over to the backup pumps. So you're seeing the redundancy. Not only do we have System 1, System 2, and System 3, so we got 3 hydraulic systems, all of which can fly that plane, but you also have several pumps within those systems that are redundant to each other. So a lot has to go wrong in order to not have a functioning hydraulic system and or pump. Okay, So,
Adam,
yeah.
that was one of my questions at the bottom line there. It says backup pumps B supply supplementary pressure, but what you just indicated is they only come on if the pumps 1 and 2 fail. They're not working at the same time, supplementing the pressure.
Yeah, so the backup pumps, they do, they will assist some, like on takeoff and landing, like it says, or if the pilot manually turns it on from the cockpit. But just because takeoff and landing are your primary, like when the only reason they're really turning on during takeoff and landing is because those are the two really critical phases of flight. And it's really not that they need to be on, but they're on in case it fails. Does that make sense? So that you don't have a lag in if one of the A pumps fails, that there would be a little bit of a lag time to get the B pump turned on and pumping stuff again. And that's only during takeoff and landing, because if one fails there, a couple of seconds waiting for that pump, and if it's affecting, you know, your aileron, let's say, or your your rudder, and you're really close to the ground, well, that can be the difference between crashing or landing. So they're on to supply the supplementary pressure during takeoff and landing, and it's just extra pressure in case the other ones fail. Then it already has additional pressure to it, and it really won't notice a drop off because they're already on and functioning.
Uh, Thank you.
Yeah. So let's take a look at what they operate. So systems 1 and 2 are similar in operation except for reservoir capacities. Hydraulic system 1 powers the rudder and elevators, the left aileron, the outboard multi-function spoileron panels, the outboard ground spoilers, and the left thrust reverser. Okay, you don't necessarily need to memorize that. If you want to come back to the PowerPoint, it is obviously in the folder for today's stuff, but let's take a look at System 2. System 2 also powers the rudder and elevators, the right aileron, the inboard multi-function spoiler panels, landing gear alternate extension, the right thrust reverser, and the outboard brakes. Systems 1 and 2 are cooled with a heat exchanger. Okay, so a lot of the stuff, memorizing what these systems power, you don't need to do that. In fact, if you walked into SkyWest, you couldn't walk up to a dispatcher and say, "Hey, tell me what hydraulic system 2 powers." They wouldn't even be able to name one thing. So you don't necessarily need to know that. So in that they're cooled with a heat exchanger, same thing. Don't necessarily need to know that. We're just kind of covering it in here. So let's talk about System 3. System 3 uses 2 electric pumps. Okay, so let's take a look at. So remember, System 3 is really the backup, the main backup system. So it powers. You'll see kind of now on this one. You'll see if System 3 is on, it does rudder and elevators, left and right aileron, the inboard ground spoilers, landing gear, nose wheel steering, and inboard brakes. Now, those items are considered your minimum flight control needs. Okay, so if you lost power to System 1 and 2 and you were using System 3, System 3 only powers the necessary flight control systems that you need in order to safely land the plane. So there will be some stuff that is not getting hydraulic power when only System 3 is on. And like I said, if you're down to one hydraulic system, then that is already an emergency situation, and your instructions in that case is to land at the nearest suitable airport. Okay, so System 3 is only going to give you the power to the absolute bare minimum flight controls that you need to get that plane down onto the ground. But you'll notice that whereas system 1 and 2, like system 1 was just the left aileron, system 2 was just the right aileron, system 3 is both. Okay, so system 3 does both. It does the landing gear, so you need that. You need your rudder, you need your elevators, you need your ailerons. That's what flies the plane. Once you land, you need those ground spoilers to stop. Obviously, you need the landing gear. And then your Nosewheel steering and your inboard brakes. Those are really the bare bones necessities to get the plane on the ground and steer it off the runway. That's about it. System 3 has no special provision for cooling. So then this next little bit here, emergency electrical power from the ADG is provided directly to pump 3B to maintain hydraulic pressure to the flight controls during a loss of AC and engine power during flight. Okay, so have you guys, refresh me, did you guys already talk about the power plant system? Like the engines and what's providing power and electrical power to the plane?
Are you referring to like the APU?
Yeah, like any of that system. So like your your power generators, like your engine driven generators, IDGs, the APU, the
Yes.
ADG. Okay, so you guys did talk about that. Okay, so let's just talk about it for a second here. Let's have a quick refresh. Okay. The CRJ 700, your primary source of power are going to be your integrated drive generators. Okay, they're engine driven generators essentially. So each engine has a generator on it. Okay, it's if you think about a car, it's pretty similar. A car has an alternator, right? Which basically is generating power. It's providing that electrical current to power up things inside the car. It's kind of the same deal. If the engine's not working, then the alternator's not working, right? It's not spinning it around to provide that current. Okay, the only thing you have outside of that in a car for electrical power is if the alternator's not working, then you're down to just battery power, just your car battery. Okay, if the alternator's not working, it's not charging the battery, which so over time, you can kind of see if the alternator stops working, then the battery will stop charging, and then eventually the battery is going to go dead. You're going to lose that. So obviously, airplanes are a little bit more have a few more extra things than a car, but they work the same way. Okay. Your primary sources of power are these engine-driven generators, which is essentially kind of like an alternator. Okay, that's your primary. So when everything's going good and everything's functioning normally, you've got a generator in each engine, and each of those generators powers up the entire aircraft. Everything, right? Every light, every bell, every chime, everything that you hear, see, do on an airplane that has anything to do with electrical power comes from those engine-driven generators, the IDGs. Okay, so those are your primary sources of power. In addition to those primary sources of power, you also have an APU, which stands for Auxiliary Power Unit. Okay, so the APU is for auxiliary power. Okay, so the problem with the engine driven generators is that when the engines aren't on, they're not providing power. It's the same deal like a car, right? If your car engine is not on, the alternator is not giving you power. That's why we can't just jump in our cars and just turn the key to the on position without starting it and just leave it sitting there. Why? Because our batteries would go dead, right? Same idea. In an airplane, if the engines aren't on, which if it's on the ground and it's at the gate, typically the engines are not going to be on. So you do not have the power source of those engine driven generators when you're on the ground at the gate or if you're parked. So instead of just using battery power like a car would, an airplane has this APU system. Okay, an APU is essentially, it's like a mini jet engine, except it's up in the back tail section of the aircraft, or sometimes either just the rear part of the aircraft, sometimes kind of up into the tail section, just depending on the model of aircraft. But anyway, all that thing does is it provides auxiliary electrical power. So it's like a little mini engine that starts up, and it's kind of like a little generator, and it provides power. And it can also power up the entire plane, and it's really meant to be used when the engines are off. Once you push back from the gate, start one of the engines, you'll normally turn the APU off at that point because you have an engine on, so you can power up the aircraft electrically from just one of those engine generators. So as soon as you start one engine, the APU usually gets turned off. The APU has a few other functions as well, which we'll talk about in different systems, but talking solely of the electrical system, your APU, is that auxiliary power, supposed to be used on the ground. If you were to have an engine driven, if one of those engine generators were to fail during flight for whatever reason, then the APU also would act as a backup to that. You could turn on the APU in flight and have it cover for that one generator that went out. Okay, so once again, redundancy. The FAA tells us that we have to have pretty much two of everything operating at all times. Okay, so whether that be hydraulic systems, whether that be electrical systems, anything you want to name, there has to be two functioning systems. Okay, so when you're up in the air, you have the two engine generators. Normally they're functioning. As long as those two are functioning, you're good. Okay, as soon as one of them goes out, though, you're down to just one generator working. Well, now, in order to maintain the regulation, you have to have another system in there. So that's when you fire up the APU, turn it on. Okay, now we have two again. We've got the APU and one of the engine-driven generators. Okay, now if for whatever reason, if the other engine-driven generator failed, now you're down once again to just the APU working. So you're down to one system. You can't just have one system. When you're down to one system, that means declare an emergency, divert to the nearest suitable airport immediately. You'll notice that that's a common theme with anything. Okay, let's go back to hydraulics for a second. You always have to have two hydraulic systems functioning. If one of them fails, then system 3 has to kick in and cover for it. So as long as you have two of the systems functioning, whether it be 1 and 2 or 1 and 3 or 2 and 3, whatever, you have to have two. If you get down to the point where you just have one and you don't have one that you can fire up or has a backup, anytime you're down to one, it suddenly becomes an emergency situation, which means, in any of those mechanical situations, you're supposed to divert to the nearest suitable airport. Okay. So, like I said, if you're down to just System 3, then System 3 is only operating just those basic flight control items that are going to help you land the plane, get it down onto the ground. But, like I said, if you're only on System 3, you can already assume that you're declaring an emergency and diverting to the nearest suitable airport, right? Because you only have one system. It's the same thing with the electrical system. So you always have to have two operating. Usually it's the two engine-driven generators, but it's not uncommon to see one of the engine generators out of service or not functioning. And you can fly the aircraft without one of those engine generators working. We can take people on it. We can fly it as a 121 plane. Once we jump into MELs later on, you'll see how we do this. Okay, but for now, you can fly a plane that if it has a generator out, or even going back to the hydraulic system, if it has a hydraulic system out, you can still fly the plane, but what you're doing is you're starting out using your backup system. Okay, so you're starting off, there's your two that you need, okay, but if one of those fails, then you have no backup. So an aircraft that has an engine generator out or a hydraulic system out to begin before it even starts the flight is already kind of handicapped in a way, because if it gets up in the air and one of those other systems has a problem, then where normally you would have a backup, you don't have your backup in place in that situation. So you would it would be an immediate emergency diversion in the for that type of a situation on that aircraft. So anyway, but going back to that electrical system, the APU is the backup. Okay, you turn that on. We also use it as the primary electrical system on the ground when the engines aren't on. Now, if you were to get into a total worst case scenario, the engine generators are both out, the APU is out, then in that situation, the only thing you have left to provide an emergency, now this is your emergency source of power, is that ADG, the air-driven generator. Did Garrett show you guys what this is, show you a picture of what it looks like? It's like a little windmill thing that pops down below the first officer's seat. It's like, it's on the outside of the plane, obviously, but it's directly below him. But it pops out, and it has these little fan blades, and it just turns into a windmill. It catches that air as the plane's flying through the air, and it spins the windmill, essentially. And just like a windmill does, it creates, a natural source of electricity just by spinning the windmill. Now, but you guys do remember talking about this?
Just yesterday.
Good deal. Okay. So that's the ADG. So if you're down to just the ADG, then yeah, you know that you're kind of in a, that situation again. You're declaring an emergency, you're going to the nearest suitable airport. The ADG, so that's kind of why I wanted to touch on it, so that you can understand what's going on. That's the big thing here, is I just want you guys to understand what's going on, what's the thought process as far as the plane is concerned. Okay, so emergency electrical power, ADG, is provided directly to pump 3B. Okay, so when you get down to where you only have the power from the ADG, the APU is out, the engine-driven generators are both out, then you're just the ADG. The ADG, the only thing it powers is only hydraulic pump 3B. Okay, that is the only thing that it's going to power up. And 3B powers up enough hydraulic pressure to the flight controls, kind of those, once again, those minimum bare bone flight control systems, in order to get the plane down onto the ground. Okay, so the ADG works kind of like System 3. It's only powering up certain things. The ADG only sends power to System 3. It doesn't even send power to to System 1 and 2. Now, when you start thinking about it logically speaking, if System 1 is out, that's going to be because that engine failed, or the second engine failed. That's automatically going to take your hydraulic systems out. That's why the ADG doesn't even bother powering up System 1 or 2. Okay, because it knows that if it's down to using the ADG, that hydraulic system 1 and 2 most likely aren't even working anyway. So it only sends power to System 3, and System 3 isn't connected to an engine, and that doesn't have any hydraulic or engine-driven pumps. It only has the electric pumps. So you can kind of start seeing, how much has to happen in order to not have electrical power, to not have hydraulic power. You can cut, I mean, you really have to be in a very dire situation. It's hard to bring an aircraft down. Hopefully, as we go through the systems, you guys will start seeing this, why planes don't crash, and why you can have, like a couple of weeks ago, if you guys saw that Southwest flight that had the uncontained engine failure. The entire engine, it blew up, right? I mean, and the fan blades went into the fuselage. Obviously, that lady died, got kind of partially sucked out of the plane. Anyway, you can see what can happen. 30 years ago, if that happens 30 years ago, that plane crashes. And everyone on board that plane dies, most likely, in that same situation. And they call that uncontained engine failure. When you have engine failure is one thing on its own, okay? But uncontained engine failure, so regular engine failure, when I was talking about those statistics of seeing maybe 5 or 6 a month out of 60,000 flights, that's just engine failure. In my entire career, and I don't have 6 years of SkyWest and a few other years at other airlines, but I've never dealt with an uncontained engine failure. Uncontained just simply means where the engine literally comes apart or explodes. All other engine failures, that doesn't happen. It just simply means that the engine stopped working or it turned off for whatever reason, but nothing came apart, nothing blew up. Uncontained, when you hear the word uncontained in front of engine failure, that means that the engine literally came apart at the seams and wreaked havoc, exploded. You don't see that very often. That is extremely rare. And for the fact that it's happened twice to Southwest Airlines in the last 2 or 3 years is kind of crazy. There was one, I think last year, it was an A380. I think it was an Air France A380. A380, for those of you that don't know, is the largest aircraft, people carrying aircraft in the world right now. It's the double-decker Airbus. Anyway, it has 4 engines, and one of those engines had an uncontained engine failure over the North Atlantic. And, but it still had 3 other engines. In the case of Southwest, they had, you have an uncontained engine failure, but you still have the other engine as well, which, like I said, all these systems, they're not connected to each other. Those engines are totally separate. All of the systems within those engines are not tied into each other. So, and for good reasons, right? I mean, you want them independent so that they don't rely on the other engine. So if you lose an engine, it's if you get an engine failure, you can always assume that whatever happened to that engine has to completely, and if you were to have the same thing happen to the other engine, you can always assume that it is completely unrelated. Now, when I say unrelated, I mean like the fact, like if you look at the Southwest flight where the fan blades came apart, like so you would have to, the coincidence of having that in both engines happen obviously would be extremely rare. So when you have an engine fail, the odds of having the other engine fail as well are extremely rare because there's not one thing that has anything to do with the other engine on either of the engines. So they're completely separate from each other. So you would have to have 2 totally different individual things going on in order to cause both engines to fail, right? Now, if you go back to, say, the U.S. air crash that landed in the Hudson River back in 2009, I believe that was. Now, that had a double engine failure, but what was the reason? Well, it's because they went through a flock of geese, right? And now that makes it a little less rare. It happened, it was connected in that point, but it was because geese went into both engines, right? So if one thing happens to one engine, it won't have any effect on the other engine. That's all I'm trying to say here. So that's typically when this kind of stuff happens. You know, if you're getting if you're getting multiple engine failure, you can assume that it is something going on outside of the workings of the engines. You know, like like you're flying through volcanic ash, or you're flying through a flock of geese, or there's a fire on the aircraft in the cargo hold that's melting all the lines, you know, or something like that. Like it's something unrelated to the engines if you're having more than one engine failing. So you know, you can kind of see, once again, these things are totally redundant, and it takes major acts of God to bring these things out of the air. You know, you can have an engine blow up and it'll still land safely, and that's because of the redundancy. So yeah, like I said, 30 years ago, if that happens, most likely the entire plane comes down. So let's continue on here. So that pretty much covers it for hydraulics. Any of you guys have any questions on that? Let's jump into ice and rain protection. Okay, this first little part is something you're going to need to know. Ice and rain protection key points. So the CRJ 700 has systems built into it to prevent ice from building up, and also to remove ice that has built up. It also helps that as well. So one thing that you guys need to understand about anti-icing, this is basically your anti-ice system, or the ice and rain protection system. A lot of people think that ice on a plane is bad. Okay, now I don't want to confuse you. It is bad to have ice on a plane. However, there's only certain places that we care about ice being on a plane. You can have ice and snow all over the fuselage of the aircraft. Okay, it can be all over it. You can have an inch of ice on your window, all around the entire airplane, every single window, and it's not going to, other than adding weight, which adding extra weight can obviously affect things, but aerodynamically speaking, ice on the fuselage and other non-critical areas of the airplane don't do anything to the plane other than just add weight. The only areas of the plane that we care about ice not forming are, and these are the ones that you're going to want to memorize and know, are the wing leading edges, the slats and engine intake nose cowls. So the wing leading edges and the slats and engine intake nose cowls, okay? Those two areas are anti-iced using engine bleed air. Okay, so that's basically just the inlet to the engine. It's that outer circle. Like if you were to be looking at the engine, you could see around the edge of that inlet, it's like a metal little frame around it, and that's because it heats up. And the same thing on the front leading edge of the wing, you'll see that same metal material along that front edge of the wing. And it's for the same reasons. That's because if you're flying and you turn on the anti-ice system, that heats up and it melts ice and it prevents ice from forming on the front of the wing. We don't care about ice on the bottom of the wing or even, on other parts of the wing. It's really just that leading edge that you have to keep clear of ice. If you keep the leading edge free of ice, it's usually going to keep everything behind it free of ice as well. So the way that it's anti-iced is using engine bleed air. So the engines these big jet engines produce a lot of what we call bleed air. And I'm not sure if you guys have talked about bleed air yet or not, but this bleed air, we use it for a lot of different things. It's if you don't use it for something, it's just wasted essentially, because all of the air traveling through these engines, a lot of it is used, obviously to do, like the fuel combustion and, to the actual mechanical part of the engine to create thrust and stuff like that. But there's a lot of air that moves through the engines that's not used for anything. It just comes out the back, and it's really wasted unless you find something to do with it. Every engine only really uses about 20% of the air coming through it for actual thrust, for actual power to move the aircraft forward and fly. So, but if you think about 80% of the air coming through there is not used for power. It just goes through, and unless we find a way to use it, it's used for nothing. So now it's also good to know that bleed air is extremely hot. It's going through the engine, and it does heat up. You're talking 1,000 degrees or more is the temperature of this bleed air. So what they did is they take this bleed air, they harness all of this extra air coming from the engines, and we use it for certain things. We run it through. Well, first of all, we obviously use it for anti-icing. They use these little metal tubes, and they run those tubes down the front of the wing. They run it up around the engine inlets. They run it up to the horizontal stabilizer up on the tail. You'll also see that area is anti-iced, but they send this really extremely hot bleed air to those areas to warm up those surfaces to melt ice, or even just keep them warm to prevent ice from forming. And then we also, that's one of the uses for bleed air. Other uses, we obviously use it for engine starting. The engines need air blowing through them in order to start. We normally get that air from the APU. When we back up, when we push back from the gate, the APU is usually the only thing working. And like I told you guys, the APU is like a mini jet engine. So it also produces this bleed air. And the way it's designed is they take the bleed air from the APU and they run it, and they use that bleed air to start the first engine whenever, when they first start up one of the engines. They use the bleed air from the APU to do that. Once that engine is up and going, that engine now is producing some bleed air. So they take that bleed air and then they send it to the other engine to start it up. And then they usually turn off the APU. But then you have that bleed air coming from the engines. They use it for the anti-icing. They also use it for the pressurization system. Those are a couple of the uses for it. So the windshield is also an area that we want to keep ice off of, and not because it has anything to do with the aerodynamics of flight. It's just simply obviously to have visibility for the pilots. So we want the windshield free of ice, and then the only other critical areas on the plane are the little probes, the air data probes that measure pressure. They measure wind speed, air speed, all of that stuff. If ice builds up on those, you'll get incorrect readings, and it'll show different altitudes and things like that are inaccurate. So we got to keep those warm. And the windshield and those air data probes, they just simply heat up using electrical power. So the engine bleed air is only used for the wing leading edges and the engine cowls. And we have wipers, which remove rain and snow from both of the pilot and co-pilot's windshields. So in a nutshell, that's your ice and rain protection system. There's some other systems in there that are called ice detection systems. They are installed one on each side of the forward fuselage to alert pilots of impending ice conditions. So there are these little sensors that can tell the pilots when ice is forming on the aircraft, or they kind of give them a heads up. The anti-ice ducting is continuously monitored for bleed air leakage. So kind of what I was telling you, they use those tubes to carry that extremely hot bleed air to the wing leading edges. If you opened up the wing, you could see all these metal tubes running through that area, and that's your bleed air running through the anti-ice system. However, because that air is so hot, it's really common because it's so hot that sometimes it melts little holes into those tubes. And when you get holes in those tubes, you get obviously a bleed air leakage. So an aircraft can have a certain amount of those tubes with leaks in them. But once you get over that threshold, then the anti-ice system is considered inoperative. You can't use it. And then you obviously got to get it fixed. But just know that you will see that a lot. You'll see these mechanical problems with the airplanes, and like I said, unless they're over that threshold, then it's not going to prevent the plane from flying. It'll still be able to fly and carry people, but if you continue to have more problems and more leakage spots, then eventually it's going to go beyond what that threshold is, and then they'll have to fix them. So, but yeah, you'll see these little leaks, and that's just simply because the air is so hot in there. It does melt that tubing over time, and then they have to constantly fix it. But there's a system in there that monitors for bleed air leakage, so it can monitor the pressure of the bleed air coming through the tubes, and if it senses that pressure has decreased, it can only assume it's because there's a leak somewhere. So. The cockpit windshields and windows are constructed of 3 laminated glass panels separated by 2 vinyl layers. The inner surface of the outer glass panel has a conductive coating that is electrically energized for heating. That's kind of what keeps the windshield warm and prevents ice from forming on it. Any questions about the ice and rain protection system? Okay, let's talk about the indicating and recording system. This is the ICAS, okay? The ICAS system is basically, if you're in the cockpit, you see you pretty much kind of just assume they look like computer screens that they're looking at in there that have all sorts of different information on them. Okay, that is the ICAS system. Then you have ICAS system and ICAS panels, and they basically show us different things, but let's jump in and take a look here. So the indicating and recording system consists of components that display or record critical aircraft information and system operation. The function of the ICAS is to display the engine instruments, visual and aural crew alert messages, and real-time interpretation of aircraft system operation. So this is basically a system that's kind of monitoring everything, and if something's going wrong, it'll display messages and give aural warnings, visual warnings, but it'll have those visual warnings on those screens, and then it'll also, if it's an aural warning, you'll hear it say something, there's a lot of aural alerts that can go on in a cockpit for several different types of reasons, but like when you turn, like one of these aural alerts is when you turn the autopilot off and on in the cockpit, it displays the message on that ICAS screen where it'll say autopilot off, and then but then as it turns off, you'll hear like an aural message of kind of a voice thing in the cockpit which will, it'll say, autopilot off, or you'll hear like a series of beeps, which means the autopilot's turning off. So, those aren't things that the dispatcher necessarily needs to memorize what the RO alerts are, but just know what the ICAS system is all you really need to know. The Engine Indication and Crew Alerting System, that is what ICAS stands for, but it provides automatic system monitoring, the integration of system monitoring, color logic for presentation of minimum and maximum limits, and RO alert warning messages. Information is provided on 2 cathode ray tubes located on the center instrument panel. Master warning and caution lights located on the glare shield. The crew alerting system provides visual and RO alerts when data concentrator units detect a malfunction. The 2 data concentrator units collect data from various aircraft systems, processes the information, relays it to the proper component for display. And the CAS prioritizes messages by order of occurrence and order of importance. So this is kind of where all the warning messages are coming up. So like if you had, hydraulic system 1 failing, you'd get a little warning message on the ICAS system right there that says hydraulic system 1 fail. It'll say it right on there, and it'll be in red. Or, engine fail. It'll also warn you there as well. And anything that's going on, it's going to go through this ICAS system and be displayed. If it's something the crew needs to see, it'll be displayed on that screen. There's 4 levels of CAS warning importance. Red means warning. That means something already has happened. Be aware your engine has failed. Amber means caution. Caution is something may happen. Hasn't happened yet, but it may happen. It might be about to happen. Green is an advisory message. Kind of more just like, hey, heads up, be aware of this. Not really an issue yet. Could be down the road. And then status is white. So you turn the autopilot on and off. That's just going to be a white message. It's not doing anything. It's not something that you need to take a measure with. But when you get all the way up to red and it's warning, that means you need to do something. Even the caution, the amber one, means, hey, you need to do something. Otherwise, this is going to turn into a warning. A lot of times, you'll see a caution first ahead of something about to happen. And then once it happens, you'll see the red actual warning come on. The primary page of the ICAS system measures the N1 speed, the ITT speed. You don't necessarily need to know all these, but N2 speed, fuel flow, oil temperature, oil pressure gauges, vibration gauges. On the status page, you get the CAS advisory and status messages, the APU status, your flight number, trim settings, crew oxygen pressure, cabin pressure and temperature, brake temperature. And then you have synoptic pages. And you can scroll through all of these different pages to look at different systems. So you have a page for the ECS, which is the environmental control system. That's basically your air conditioning, your pressurization. Then you have a page that covers the hydraulic system, right? So you can see system 1, 2, and 3. You can see all 6 of your pumps on there. If they're operating, which ones are not operating, which ones are. You've got a page for the AC electrical system and another page for the DC electrical system. A fuel page shows you all the remaining fuel, in what tanks are they in. And then a flight controls page, anti-ice system page, and the doors page. The doors page will show you if any doors are open, like, hey, if you're getting ready to push back and you're wondering why, what's taking so long, well, you can go to the doors page. You can see that the cargo door is still open. They might still be loading bags. So you can see which doors are open. and then obviously all that other stuff we talked about. So the ICAS message inhibit logic. It minimizes spurious or distracting warning or caution messages during the initial takeoff and final takeoff and landing phases of flight. So it's basically saying if you're rolling down the runway, it will recognize that, and it's not going to do like one of its annoying messages or one of its aural warnings right as you're rolling down the runway. You can imagine you're about ready to pull back the yoke, and then all of a sudden you get like warning. It could freak you out, and it can cause you to mess up and go off the runway or do something weird, So it basically is saying that the ICAS system will recognize when the aircraft is in those phases of flight, and it will not spur a warning during that in order to not distract you from what's going on. The FDR, which is the flight data recorder, that's part of the black box that we always hear about. It records the last 25 hours of flight data using solid state memory. The maintenance diagnostic computer, the MDC, records engine and system parameters, and data can be downloaded for system diagnosis and fault identification. So these are additional parts of the indicating and recording system. So you have all that ICAS stuff that we talked about. These are additional things. The FDR, the flight data recorder, the FDR is recording everything that's going on in the plane. It's recording the altitude, the wind speed, the airspeed, true airspeed, indicated airspeed, flap settings, anything that can be modified, adjusted, anything going on. Every measurable element of flight is being covered in the FDR. Like I said, the FDR is part of the black box. The other part of the black box, which I think we're going to be talking about here in a minute, is the cockpit voice recorder. But let's talk about the maintenance diagnostic computer, which is another part of this system. It records all the engine and system parameters, and so if something's going on or whatever, the plane lands and it goes into a maintenance base, they can take a computer over, hook it up to this MDC, and that computer is going to tell them, hey, this is what's going on. Landing gear. So the landing gear key points. The CRJ 700 has a standard retractable tricycle configuration. Hydraulic System 3 powers the landing gear and the Nosewheel Steering. So based on what you guys know of Hydraulic System 3, why do you think Hydraulic System 3 powers the landing gear and Nosewheel Steering?
Used only in emergencies. You need to get the gear down.
Yeah, I mean, we obviously use it on every flight, the landing gear and the Nosewheel Steering, but it's basically saying that Hydraulic System 3, which is the system which is the backup to the backups, the last one to go down, is the system connected to the Nosewheel Steering and the landing gear, because they are considered part of those essential items you need for an emergency. Hydraulic Systems 2 and 3 operate the brakes. You have a manual gear extension available. That's just in case the regular one's not working. You can do a manual gear extension. They have main landing gear overheat detection. So the reason there's overheat detection is because it's really common. These tires on these aircraft, as you are doing a takeoff roll, they get spinning really fast. You're getting up there 150 miles an hour rolling down this concrete runway. those tires, they're really going fast and they get really hot. And sometimes what happens is if depending on the weight of the plane and obviously several other factors, but because they're cruising down that runway, that the rubber on those tires heats up really, really hot. And as they retract the gear, it obviously comes up into the plane, into the landing gear bay. And those tires remain really hot for quite a while. And they, in some cases, they can actually cause fires because they're so hot. If they get up there and, they got too hot, and, they can actually catch on fire. And then, that's how sometimes you get stuff down in the cargo bay on fires because of the landing gears. But anyway, there's an overheat detection system which will tell you if it gets too hot in there. So just to kind of give you an idea, I'm not sure if any of you guys heard, this is several years ago, but there was like a young kid that jumped the fence somewhere. He was either running from somebody or running away from home or something, something apparently bad going on in his life, but he jumped the fence at the Oakland airport out in California and ran and hid in the landing gear of a Hawaiian Airlines flight. And he crawled up in there, and I guess apparently like fell asleep or something, but that plane eventually pushed back and it left, it took off. And several things that could possibly go wrong there is the area where the landing gear comes up, those landing gear bays, those are non-pressurized. So, you get up too high, get into the wrong situation, you're usually not going to have any oxygen because there's no pressurization in there. Second thing, because there's no pressurization, that also means there's no temperature control. That means you get up to 35,000 feet, it's going to be potentially negative 50 degrees. So it was kind of an amazing story, though. This kid runs across and he hides in the landing gear bay. And the plane, he ends up falling asleep or whatever, and the plane ends up leaving, going to Hawaii, goes all the way to Hawaii, and they get to the gate, and then they notice this kid jumps out, and they catch him, basically, and figure out where he was from, figure out that he got on the plane in Oakland. Then they're trying to figure out, how did this guy live? How did this kid survive? And the only thing that they can think of is that the landing gear usually stays warm for quite a while, but that landing gear provided enough warmth for him to survive falling asleep down inside the landing gear bay and surviving all the way to Hawaii. As far as the oxygen and the pressurization thing, that was another different thing, but yeah, I guess it's not unheard of that people can survive, up to 30,000 feet. But pretty rare. So kind of a weird story, but just kind of gives you an idea. I mean, a flight all the way to Hawaii, it stayed warm enough long enough for this kid to live. The Nosewheel steering is hydraulically actuated and accomplished using a steering tiller or movement of the rudder pedals. So that's just a little thing. This is a little like mini steering wheel up there attached to the front wheel and helps the plane turn and stuff. There's dual channel inboard and outboard anti-skid system. That's basically just to help the plane not skid when it lands. The BTMS, which is the brake temperature monitoring system, monitors the temperature of each brake. It's displayed as a color-coded numerical readout on the ICAS status page. So sometimes those brakes can heat up a lot, especially after you land. The plane lands, they stomp on those brakes, and those things can really heat up. So it's just basically letting you know if the brakes get too hot. Then there's a tail skid plate, which is installed on the aft fuselage and prevents the tail cone from making ground contact in the event of a high rotation pitch angle during takeoff. It's basically, yeah, it's just this little knob on the back that if the plane rotates too fast, it will hit that knob and just, drag along the concrete instead of actually hitting the fuselage and causing damage. Okay, let's see. Aircraft lighting. Let me see how long this one is real quick. Okay, cover aircraft lighting and then we'll call it a night. Aircraft lighting. So the lighting system includes external lighting, flight deck lighting, passenger compartment lighting, service compartment lighting, and emergency lighting. The lighting for aircraft visibility. The aircraft has navigation lights on the wings. It has anti-collision strobe lights, has a rotating beacon, which just means that the engines are operating. It has logo lights, wing inspection lights. The wing inspection lights are to turn on at night to make sure that ice isn't forming on the wings. It's so that the pilots can see the wing at night, essentially. It also has taxi recognition lights, nose landing lights, wing landing lights, and wing inspection lights. Those are the external illumination. Emergency lighting, the wall and floor level exit signs, ceiling and floor level emergency floodlights, and then there's floor track photoluminescent tape. It's obviously for when there's any sort of an emergency on the airplane and you lose power and you're wondering which way you need to go to the nearest exit. You look at those little things and it will illuminate your way out, I guess. There's also the emergency lights inside the inside the cabin and the cockpit. Okay, so we'll leave it off there. Start off on the navigation for tomorrow. Anybody have any questions on anything?
Nope.
Okay.
Need to soak it in.
What's that?
Need to soak it all in.
Yeah.
It's good color commentation, commentary.
Good deal. We like to provide, any insights where I can. Some of the systems really don't mean much to us. Some obviously more than others. Navigation, when we get into that tomorrow, it will have some good stuff. But yeah, the big thing about systems in general is just knowing what it means to you as a dispatcher and knowing your role, becoming familiar to the standpoint of you knowing what you need to do when those systems fail. Because, like I say, you're usually going to be the first point of contact when anything goes wrong. So that's why we need to know about these systems and what to do and how to handle the situations around their failures. So good deal. Well, if nobody else has anything, I'll let you guys go for the night. And yeah, so you guys all have a good night, and we will talk to you guys again tomorrow.
Thanks, Adam.
Good night.
Thanks, guys.